When an airplane flies, it's not just a machine. It's nearly 300,000 kilograms of metal defying the pull of gravity. How did humanity achieve something that seems impossible at first glance? In this video, we'll explore a few theories that explain how an airplane flies, and we'll debunk one popular theory that has been taught in textbooks for years. Whether correct or not, every theory revolves around one key factor: the flow of air, or any fluid, around a solid object. By understanding how air interacts with these objects, we can harness this knowledge to make a 300,000 kilogram machine soar against the force of gravity. Let's explore how air behaves around a simple object, a sphere. By observing this, we'll uncover a crucial phenomenon called the Coandă effect, which plays a key role in how airplanes fly. Take a look at this simulation of air flowing around the sphere. You might expect the air to break away from the surface, like this, but instead the air follows the contour of the sphere, almost as if it's sticking to the surface. In fact, it is sticking to the surface. This tendency of a fluid to cling to a solid body and follow its shape is known as the Coandă effect. You can observe this phenomenon in everyday life when you pour a liquid from a glass. Notice how the liquid tends to stick to the surface of the glass, making it a bit tricky to pour it cleanly into another container. The Coandă effect exists because every fluid has a property called viscosity, which is its resistance to flow. This resistance gives the fluid a kind of stickiness. For example, a highly viscous fluid like honey has a greater tendency to stick to surfaces. Even a fluid as light as air has enough viscosity to exhibit the Coandă effect, allowing it to cling to and flow along surfaces. For an airplane to fly, we need to generate a force called lift, which acts upward to counter the downward pull of gravity. To achieve this, the wings are designed in a special shape called an airfoil, which looks like this: a somewhat water drop-like shape with usually a greater surface area on the top side than the bottom side. Now, when air interacts with this airfoil, it somehow creates the lift force needed to keep the airplane in the sky. Next, let's explore how this airfoil achieves that by examining the different theories proposed. The first theory we'll examine uses Bernoulli's principle to explain how lift is generated. If you're not familiar with Bernoulli's principle, here's a quick overview. It states that when a fluid flows with no external forces acting on it, the total energy of the fluid remains constant, distributed across three factors: its height, speed, and pressure. This energy can shift between these factors as the fluid moves. Now, according to this theory, when air flows around a wing, it splits into two streams, one moving over the top and one beneath. The theory suggests that the air above the wing experiences lower pressure than the air below, creating a suction effect that applies an upward force on the wing, generating lift. But why does this pressure difference occur? Let's turn to Bernoulli's principle for the answer. In the case of a wing, we can neglect the height component, as the small difference in height between the top and bottom of the wing doesn't significantly affect the energy. This leaves us with one key factor: the velocity of the air. To maintain the total energy balance, the air above the wing must flow faster than the air below, leading to a drop in pressure above the wing. It's true that the air flows faster over the top of the wing compared to the bottom, but one theory that has made its way into many textbooks, the equal transit time theory, attempts to explain why. This theory claims that the two airflows, one above and one below the wing, must reach the trailing edge at the same time. Since the air on top has to travel a longer distance, it would need to move faster. However, this theory has been debunked. There's no reason why both airstreams should meet at the trailing edge simultaneously. In fact, experiments have shown that the air on the upper side reaches the trailing edge much earlier than the air on the underside. So the theory based on Bernoulli's principle attempts to explain lift by highlighting the lower pressure above the wing due to the faster airspeed. However, as we've seen, the reason for this is not the equal transit time theory. Many researchers advocate for the next theory we're about to explore, as it offers a more intuitive and physical explanation for why an airfoil generates lift. This theory is grounded in Newton's third law and incorporates the Coandă effect that we discussed earlier. As a quick refresher, Newton's third law states that every action has an equal and opposite reaction, much like in the case of a rocket, where the expanding, burning fuel is expelled from the rocket engines, creating an action force. The pushback on the rocket itself is the reaction force propelling it forward. As we discussed earlier, a fluid tends to follow the curvature of a solid structure due to the Coandă effect. Let's first observe the airflow around an airfoil with no bends. It's simple. The air collides with the airfoil and follows the path along its boundaries. Now let's introduce a slight bend to the airfoil. This setup starts to deflect the airflow downward. As we increase the bend, the deflection becomes even more pronounced. But if we make the bend too steep, the airflow will break off at the point where the curvature begins, because the viscous force isn't strong enough to keep the air attached to the surface. Now, since the wings deflect the air downward, the reaction force pushes the wings upward, creating lift. You can try a quick experiment at home to see this in action. Take a spoon and place the curved side under a stream of water. You'll notice two things. First, the water gets deflected sideways as it follows the curve of the spoon. Second, you'll feel the spoon being pulled toward the stream. This pull is the reaction force to the water being deflected away. Now, what's important to highlight is that this experiment with the spoon has nothing to do with Bernoulli's principle, since the fluid is only on one side of the spoon. There's no pressure difference here, just the physical interaction of deflecting fluid, confirming that lift can be generated purely by the deflection of air, independent of pressure variations on both sides of the object. Now let's see how we use this knowledge to make an airplane fly, using a simple 3D model. The wings are equipped with flaps, which allow us to control the bend of the airfoil. This is known as the angle of attack. By increasing the bend or angle of attack, we can increase the lift up to a certain limit. Beyond this point, the airflow will start to break off the surface of the wing, leading to a phenomenon called stall, which is a sudden drop in lift. Similarly, the other flaps on the wings serve different functions, such as rotating the airplane or controlling its nose, either pointing it upward or downward.